When you have constants and variables under a root, it's a good idea to separate them. And before I do it, I just kind of observe my situation. I will at some point have to do the cubed root of 8, which actually works out really nice. I'll have to do the 4th root of 16. That works out nice. But the cubed root of 54 is not going to be so nice because 54 is not a cube. So I'm going to tackle these a little bit differently because of the different situations. So for letter A, the idea is you want to think of these as separate multiples. You have 8, your x's, and your y's. And then we just take the cubed root of each term one at a time. So the cubed root of 8 is going to be 2. You can't cube root x squared because x squared is a square, so we just leave it alone. You can cube root 9 because you have to remember this means y to the 9/3. 9/3 is just 3. So if you can divide 9 by 3, then just do that and that will be simplified. And once you do that, you just want to reorganize your stuff. So the 2 and the y cubed would come out front. And we just copy our cubed root x squared at the end. And that's our final answer. Same approach with letter B. We're going to break it into 16 x's and y's. And then we take the 4th root of 16, which is 2. You can do 8 divided by 4, so you will get x squared. And you cannot 4th root 8 cubed, so you just leave it alone. And that one's simplified. So those problems are actually meant to be kind of quick because you didn't have to really do a lot of work for those. Now C and D, those are a little more complicated, so I'm actually going to do them using an exponential technique, and then we're going to do them again and avoid exponents just so you can see the difference and how you can handle these situations. So if you're going to play the exponent game, you need to change 54 into a product of primes. So if you broke down 54, you would end up with 3 3s and a 2. So that's where we get 3 cubed and 2 from. That makes 54. X to the 4th and y cubed were also under the root, so I use a parenthesis to show that, hey, all of this was under the radical. And cubed root is the same thing as a 1/3 power. So that's kind of your first step to this approach. Then you're going to take your 1/3 and you're going to distribute it to all your inner exponents. 1/3 times 3 is 1. 1/3 times, there's a 1 here with the 2. That makes 1/3. 4/3 and 1. And then you always look at your exponents and you want to make sure that they're either integers or that they're proper fractions. So right now I see that I have x to the 4/3. 4/3 is an improper fraction. So we need to break it apart into x to the 1st and x to the 1/3. Now that all my exponents are following the rules they're supposed to follow, it's time to write our answer. You have a 3, you have an x, and you have a y. Those all go out front. The 2 and the other x, however, are both to the 1/3. So that means they both go under a cubed root. And that's our final answer. We're going to do the same thing for letter D. So if I were to break down 64 until I could no longer do so, I would end up with 6 2's. So 64 is 2 to the 6. And then you have your A's and your B's. All of those are under a root, so we write to the 1/5 power. And then we distribute our exponents. And then we realize 6/5 and 13/5 are improper. So we split up our 2 into 1 and 1/5. And 13/5 we break into 2 and 3/5. Now that all of our exponents are whole numbers or proper fractions, now we can present our answer. Our 2, our a squared, and our b squared will all go out front. And then our b cubed and our 2 to the first will remain inside a fifth root. So again, I call this the exponential technique because you're using all rules of exponents and you're playing with the exponents to get your answer. The other technique you can use doesn't use exponents at all. So I'd like to show you how that works for both of these, just so you can see how one method compares to the other. So the first thing you would do is think, well, I cannot cube root 54, but there is a cube in 54. So if I think about that, I can break it into 27 and 2. There is a cube in x to the fourth. It is x cubed. So we would have to break this apart as well into x cubed and x to the first. That way 1 and 3 would make 4x's total, but I have exposed the cube. And we can do the cubed root of y cubed. That would just be y. So I broke my problem apart, I simplified each radical, and now I put it back together. So we'll change the cube root of 27 into 3. We'll change this into x, and we have a y. That will all come out front. 2 and x to the first must remain under the root. We get the same answer. The techniques are completely different. One's using all exponent rules, the other is using simplifying radicals rules. So I'll show that to you again using the next example, 64. So again, we want to break it apart into 64 A's and B's. You cannot fifth root 64, but you can divide it by 32 and 2. So there is a fifth power that goes into 64, and that's 32. We can fifth root a to the 10th. That would become a squared. We can do 10 divided by 5 and get 2. We can't do 13 divided by 5 though, so we'll have to expose b to the 13th as b to the 10th and b cubed. And I chose to do it this way because I knew that 10 was divisible by 5, and I'll have a remainder of 3. And then we simplify. The fifth root of 32 is 2. We'll have an a squared. We'll have a b squared. All go outside. The 2 and the b cubed remain inside. So I'm not going to force you to use one technique or the other. I just simply want you to see it both ways so that you have some more tools in your toolbox in case you're faced with a problem and you want to know the different ways you can handle it. In our next video, we'll go ahead and do some more roots, but this time we'll have division inside of them.